Okay, sweet. So, hello, this is Jacob and Chirag. Right now, I'm going through the feed system build process, and Chirag is learning it for the first time, so we thought it'd be a good idea to record it, and other people who want to listen to this asynchronously can follow along and learn just like Chirag is learning from the perspective of someone who's never really seen this before. We're going to go through the full feed system process and also explain a lot of this feed system design. So let's see, let me get my computer.
Yeah, we can't really go back a slide when we do this. Oh, you probably do this.
Okay. So where do we begin? With the fill state and assumptions. So when we start this feed system, you're showing up to a field, and we want to make it clear what the assumptions are on the system. So you show up to the field, you've got your nitrous oxide, your nitrogen, and your ethanol, and none of them are connected at all to this feed system. The feed system is completely open to atmosphere, whatever, it's completely powered off.
Is that what the bar
Well, let's just go to slide 2 and we'll show we'll show two things. We'll take a second on slide 2. Let's go to that right now. Yeah, so slide 2, feel free to pause and come back to this in the future. This has the key for everything you're looking at on that next, on that feed system diagram. Okay, so we can move on. Feel free to always come back to this 2-minute part of the video. Next part. So you show up to the field, and this is kind of how it looks, except there's not even a nitrogen tank connected. So nitrogen is light blue, if you can hover around that, and then yeah, from a high level, I can try to explain if I can.
This is connected to the pressure gauge over here.
Pressure regulator,
yeah.
which has gauges built into it.
Yeah.
But I'll just give a super high level overview before we go into anything. So in general, the top is the nitrous oxide system. Like that's where nitrous oxide flows in, gets filled into, and then flows through into the engine right here. The nitrogen, which is pressurizing this system, that does multiple things. It keeps nitrous oxide at a liquid, even at relatively high temps, like 20 degrees Celsius, not actually high, but just normally nitrous oxide is a gas at room temperature. So we pressurize it to keep it a liquid. And then it also is pressurized to just keep a constant driving force on that nitrous oxide during the test, so that it's forced into our little injector holes and into the combustion chamber where it can combust. On the other side, also being pushed down by that same nitrogen canister and regulated, is the ethanol part of this feed system. It's a pretty similar design. The nitrous oxide section is definitely more complicated. It's more dangerous, so we put a lot more effort into keeping it safe. But the basic principles of nitrogen and inert gas driving ethanol and nitrous oxide into the engine are the same. Okay, so you show up, you keep your ethanol and nitrous oxide far away, and you do a few things before in your pre-fill process. So again, one more high level thing. I'm going to go through the pre-fill process, the fill process, which consists of filling the nitrogen, followed by filling the ethanol, followed by filling the nitrous oxide, and then the pre-test process, and then the hot fire process. Almost all of that effort goes into the filling process. And it goes in order of like least dangerous to most dangerous. So connecting the nitrogen is like an inert gas. Then it goes ethanol, which does not need to be pressurized to remain as a liquid. And then there's nitrous oxide, which is kind of the highest pressure we see is during that fill process. So high level, that's what we're about to get into. So let's see. So your pre-fill process begins with, we'll probably have a lot more details on this in the future, but effectively it's going to be a series of checklists where you're testing each instrument and each solenoid when everything is vented open to atmosphere, and like just to see if we can turn everything on and everything's working nominally. That's important because we don't want to fill this whole system up and then realize that one of our solenoid valves is not operating properly. So we'd like to test that before we fill with anything. After we verify that everything, like that the valves are working correctly, we're verifying that instruments are working properly. So we want to make sure, hey, we know by the temperature should be about 20 degrees Celsius. Are the thermocouples reading 20 degrees Celsius? Are the pressure gauges and pressure transducers reporting into the lab jack and into the lab view, like into our GUI, that it's atmospheric pressure when everything is vented at atmosphere. So basic checks like that. Ideally, some kind of automated test that can go through all of that as a backup to like manually checking every single valve and instrument. Then we've got, we can power off the system. And we really want to make sure that this system is purged before we do anything. So nitrous oxide, the bottle should not be connected. Ethanol, the bottle, nothing should be in there. This system should be purged. It should just have atmosphere in it at worst. And what we're about to get into is our nitrogen filling process.
My bottle, can you put this thing or like the actual tank?
There. Thank you for asking. So what you're seeing there, hover around and as well as there, those are run tanks. Those will begin empty. So right now, ignore the fact that it has those colors, blue and red into it. Those will begin empty, and we're eventually going to fill them. That just shows what eventually will be included in them. But yeah, so those are run tanks, and those are much smaller. They only carry at most a liter. In reality, they'll carry just a few cups of the propellants. And most of the propellant will be stored in like separated fill canisters that are far away from this test when it's actually in operation. So the worst case scenario, if something was to explode, it would only be a very limited amount of propellant. That was not an easy design decision to make because it makes things more complicated in some ways, but it limits a worst case scenario. So yeah, that's a big design point that we push for. So, okay, we made sure nitrous oxide and ethanol are not present in the system, and we're gonna now begin the nitrogen filling process. All right, so filling nitrogen, begin ensure the system is off. Then we set the PR1, which is pressure regulator 1, hover around that, to 0 psig. That is just to make sure that once nitrogen is connected, nothing just starts flowing immediately. So it's kind of just holds it there.
Which one needs to do? RPL1.
Yeah, you can say that more clearly if you'd like. Yeah,
it just holds it between PR1 and the actual N2 tank. So it's just initially set at 0 psig, right?
Yes.
Okay.
That's at atmosphere. And what it's doing is really locking down this section. So I'm going to start controlling it as well. Both of us can control it. Great. So yeah, what you're looking at here, we'll be describing each of these, hopefully not too much in detail, but that's particulate filter 1. The purpose of that is as we're filling this whole system, there's a risk that the connection between, like as you plug something in, you capture something in the atmosphere, some particulate, or something comes out of the bottles that are pressurized that goes into the feed system, and those particulates eventually cause problems in the nitrous oxide system. We're worried about a strike of a particulate against the wall, and which it's literally like lighting a match, and causing that spark, which could decompose nitrous oxide. Okay, so we screw our nitrogen flex hose, which is connected to our nitrous bottle, our nitrogen flex hose, which is connected to our nitrogen bottle, into particulate filter 1, PF1. Then we open the bottle, and so now we pressurize to whatever the bottle pressure is, which could be, I think, between 1,000 and maybe even more than 2,000 psi, up until PR1, pressure regulator 1.
So by open bottle, does this the actual regulator that's being opened?
So regulator is staying closed, so that's why we set it at 0 psi. The bottle is we use a needle valve or whatever ball valve is on that bottle, and we try to slowly open it to pressurize up until the regulator.
So. Can you go up to the pre-filling? I think. Are purged. Okay, so ensure nitrous oxide and ethanol are purged. That just means it's not connected, first of all.
Yeah.
And how do we check if there's anything in there?
Most obviously, we can't really check that it's not connected. What we definitely wanted to do was a concern that Chirag brought up before we started recording, which actually prompted this recording, is that we don't want to open a valve that is connected to nitrous oxide or any of our tanks that shouldn't be if those tanks shouldn't exist. So I think more clearly than ensure nitrous oxide and ethanol are purged, which hopefully happens during the purge process, I think the more clear thing to say would be that ensure that nitrous oxide and the nitrous oxide fill tank, which is the separate tank that is generally stored far away and is only used during the fill process, is not connected into PF3, because we're going to be purging out and getting rid of everything that is inside of those lines, and that means we need an open hole there when we eventually start the purge process. The reason for a purge process is because nitrous oxide is an oxidizer, which is one of the 3 key elements for fire. It's oxidizer, fuel, and spark. We have plenty of oxidizer once this thing is filled. Nitrous oxide should be treated just like liquid oxygen, gaseous oxygen. It's dangerous, and so we want to make sure there's no fuel, because that limits the amount of stuff that can burn if a spark happens. We also want to limit anything that could cause a spark, which is why we have those particulate filters again. So we purge. The whole purpose of this filling with nitrogen and this purge process that we're about to go into is because we're trying to get rid of the atmosphere, even because the atmosphere itself could be seen as fuel for something that's as oxidizer heavy as liquid nitrous oxide. So we're eventually going to purge it, and then we're going to close valves as it's purging so that only nitrogen, which is an inert gas, is left inside of this whole feed system. So are you ready to go into the details? Okay. You don't have to be so.
Yes, Jacob, let's go move on. Can I graduate now?
Okay. So we open the bottle, and now we're pressurized here to 2,600 psi or 1,000 psi, but we're still at 0 psi gauge. yeah, a little information on that. When we talk about PSI, it's going to be in terms of PSIG, PSI gauge, as opposed to PSI absolute. So that means if we're at 0 PSIG, we're actually at atmospheric pressure there. At 15 PSIG, which is what we'll be at soon, we're going to be 15 PSI above atmosphere. And for your reference, atmosphere is 14.7 PSI, so just about that amount. So we'll be at 2 absolute atmosphere. And if there's a hole anywhere in that feed system, you'll have the force of the pressure of the atmosphere being forced out of that hole, which is how we're going to be purging. So now we open the bottle and we start slowly opening PR1, the pressure regulator, until we get it to 15 PSIG, which means now everything on the left is still at that really high bottle pressure, and everything on the right slowly starts to fill and pressurize to 15 PSIG. But yeah, SV1 and SV2 are normally closed. So the big thing about SV1, SV2, SV3, SV4 is that they are solenoid valves, which they're one, expensive, so we don't want to have a lot of them, and then two, they're expensive because they give us a really nice capability of remotely actuating stuff. So we can open these valves while the system, like to start the test, which is something that we want to be far away from when we're starting the test. And if they lose power, they're designed to be completely closed. And that's going to be really important because SV3 and SV4 are the main way of, or maybe even the only way of stopping the whole run tank from emptying into the engine. If we decide for whatever reason that we want to stop the test, we close SV3 first and SV4 right after that, or I guess like simultaneously we close SV3 and SV4. Because yeah, those things are like some of our primary controls to start and stop flow rate. Okay, so back to nitrogen process. So we're gonna open all these valves. So except for SV1 and SV2. So that means NV1, BV1, BV3, NV3, BV5, CV. CV, so CV1 is a check valve, so that's not something that we actually control. It just prevents backflow. Yeah, that's kind of a safety measure so that if the nitrous oxide section begins to increase in pressure dramatically, it will not get pushed backwards into the ethanol system. Yeah. So that's a pretty critical safety component to have there.
And then the same goes for BB2 and BB4. Okay.
Yeah, we're going to open BB2 and BB4. I'm just going to take a quick note here.
So open all valves besides check valves.
Well, check valves cannot be opened or closed.
So like just make sure it's like, yeah.
Okay. Yeah.
Some people might think, at least I thought, right?
I think in future times we'll just pause it there so that we're not wasting your time. Sorry.
Yeah.
Okay. So let's get back to where we were about the filling process. Okay, so we've opened all the valves except for SV1 and SV2 because those are the ones that once we open them, we are starting to purge nitrogen. So we want to have a controlled purge. So we ensure all those valves are open, including SV3 and SV4, which will require electricity to actuate. So at that point, we do need to power on the system, which is important to note. And then we open SV1 and SV2 simultaneously, which begins nitrogen purge. There's some flexibility on opening it simultaneously. We might be able to just open one at a time and purge one side of the system at a time. So that's kind of not been fully decided yet, but that's where we're at currently. So then as we're purging, once we are confident, and this is another big question, is how long do we want to purge for? We, again, haven't reached a consensus on how long we would need to actually run this at 15 psig to confidently be able to say that we removed all or most of potential fuel or atmospheric gas out of the feed lines. But once we've reached that point, then we begin to close any valves that are open to atmosphere. I made an order of this, but this order isn't fully refined. So I suggested closing BV2 first, then NV3, then NV1. So BV2, then NV3, then NV1. And what's happening there is it's ensuring that BV1 is then being vented out instead of just kind of being, I don't know, like, I want to make sure BV1 is properly vented out. Then SV3, which ensures that NV3 at that point is like the pressure is going through BV1 and NV3 there, as well as some of the other stuff. SV4 as well. So now we have a slightly higher flow rate through like through NV3 and BV1. And then the last things we close are, it looks like I already closed NV3, but last thing we close is BV5. Where's BV5? Oh yeah, BV5. That one is another point of complication because we're not sure if we'll be able to actually properly vent that area or purge that area if it pretty much just runs into a wall because the pressure relief valve will not open at 15 psig. Another point of, we're still learning there. So then we have a note to like, at this point, we've closed everything except for SV1 and SV2. And we can close those at that point. And we want to check at somewhere around there, check for nominal pressure and temperature values. We'd like to see that increase in pressure, see that there's not an obvious leak at 15 psi, because if we're leaking at 15 psi, it's not a good sign for our much higher pressures. And it's one of many times that we'll be checking, just like, do our instruments work properly as we're adding, gas and at increasing pressure. So at that point, we have hopefully reached high confidence that our system is purged and there's only nitrogen in those lines. So it's very important to note, as we're pressurizing and pushing out, we're closing, and all that's left is nitrogen in the system, and at higher pressure. So nothing should be coming in. At worst, if there's a leak, it's pushing out, just like a clean room. So now we can move on to filling the ethanol. So we're filling the ethanol next because it's easier to fill ethanol. It's less likely to leak because it's not pressurized when we're trying to fill it. So filling ethanol before nitrous oxide. Again, ensure SV1 and SV2 are closed. We isolate about however many cups of ethanol that we decide we want in our test into its own separate bottle. We bring that bottle to the test stand. We've got some kind of funnel that we pour into. It goes through the particulate filter 2, so PF2, through BV2 into that T fitting, and just, we'll have to, I'm realizing, we're going to have to open, sorry, okay. I do have this documented. I just started skipping the documentation. So I'm going to go back to the filling ethanol process. So we've isolated the 2 cups of ethanol into a bottle. Then what we do next is lower the pressure regulator to just above 1 atmosphere. We want to make sure SV1 is closed, so we're going to keep the nitrous oxide side as clean as possible. And then we're going to open SV2, and then we're going to open VV2. And as we open VV2, it's going to depressurize down to just above 1 atmosphere. So it's like lightly blowing out of that hole. And then we start pouring our ethanol in. And the big idea there is, as we're pouring ethanol through this funnel, we want to try to still keep this system nitrogen like clean and free of atmosphere. So we always want some kind of gradient that's pushing atmosphere out, even though ethanol could be flowing in. There might be some way that we want to like reduce the risk of like bubbles being coming in with the ethanol. Not something that I've thought about now, but maybe just like pouring against the side of the funnel, reducing the risk of bubbles being created and flowing in with it. So then we're opening VV2. So we opened SV2 and VV4, then we open VV2, and then we pour the whole bottle into the funnel. So sorry, I keep skipping steps, but repeating that just again. Open VV2. Sorry, open SV2. Open SV2. Open VV4. And then open VV2. And at that point, it's starting to depressurize, starting to push out, but at lower, like just above atmosphere. Then you're pouring that whole bottle of 2 cups into the funnel. It's going through the particulate filter, through VV2, and running toward that run tank that you see with nitrogen and ethanol in it. As soon as you're done, close VV2. Then you're going to close VV4 and SV2. The run tank at that point is just above atmosphere, just like we had it set from that pressure regulator. And you might want to pressurize it a little bit more. So maybe increase the pressure regulator at that point to, again, 15 psi. We just want to make sure it doesn't leak down to the point where atmosphere can come back in. So I'll make a note of that.
So if you were to explain the physics behind this. So let's say, okay, so we first isolate 2 cups of ethanol into a bottle, which is the funnel part of the entire feed system. And then lower the pressure regulator to just above 1 atmosphere. So okay, so we have the funnel over here. The lower pressure regulator, which is this thing.
Yeah.
And okay, so
let's say I don't know exactly, 16, 20 psi.
So in
absolute, so like maybe 5 psi G.
So in the pre-fill phase, whatever, I think, yeah. So these 2 are closed by the end of that, and we're setting this to just above 1 atmosphere, so we can set it up for this filling process to put it in this one tank over here.
Pretty much, we want to be able to purge out slowly while putting in ethanol, which means you don't want a really hard, like blowing out. You just want enough to reduce the risk of atmosphere getting in, and small enough that you can still pour something in.
So we have a funnel over here, and we have maybe 15 of psi G going down.
5 psi G.
5 psi, okay.
We never open SV1. That's important to note.
Because we don't want any ethanol going to this portion of the road.
That, and we also just want to keep the nitrogen side, or the nitrous oxide side, pressurized.
Yeah. So then we open SV2. So we can have nitrogen go through here, and we can have it push the ethanol through to here. Is that the purpose of that?
No,
No.
the ethanol, we'll be designing this. So this is a P&ID. It's not a geometric group representation. We'll design it so that gravity is gravity fed into the run tank. So gravity is pulled down toward the run tank, and the run tank is at one of the lowest or lower points of this filling process at the very minimum. Yeah. Yeah, it's going to be filled using gravity. At least ethanol will be. Yeah. So does that answer most of your questions there?
I just need a diagram later on. That's all.
Like you want the 3D CAD.
I'm just like having trouble understanding. Like, okay, so we have a gravity-fed ethanol thing. So it's basically like a funnel, and like
high up, and the run tank is low, and everything is downhill. Everything is flowing downhill.
Yeah. So
except this is coming off. The T fitting will go off to the side.
Yeah, that makes sense.
So if the funnel is here, T fitting can go off to the side, and the run tank will be below everything.
That makes sense.
And so T fitting will have gas coming up, ethanol will flow down into the run tank. Yeah.
Oh, okay.
Does that make sense?
So it's like you have like it's like a bottle of water, and you're like trying to empty it. That's what's happening.
Yeah.
Okay. No. Okay, so it's like you're trying to empty an entire bottle of water into a sink.
Yeah.
You need some air going inside the bottle of water so the water can come out. That's what's happening.
No. The reason why we're having air come out is just to make sure that atmosphere doesn't come in with ethanol.
Okay.
Because you can imagine that if you were to open this thing, atmosphere would rush in at the beginning, and if not, you could still, I guess you want like ethanol to like flow down the sides of the tube.
Yeah.
You don't want it to necessarily fill the tube because that would cause bubbles. So you kind of want it to flow down the sides of the tube, ethanol, and then on the sides of the tube, you want gas coming through so that the gas is going out and the liquid's going in. Yeah.
That makes sense. Yeah.
Whether that works, I'm not fully sure, but
it'd be nice to have like a ring and like an inner ring, so like the gas would come up through the center ring and like the ethanol would go flow.
That kind of defeats. I think so. We'll have to talk about that eventually. Anyway.
Experience in fluid dynamics and all that stuff. So.
There you are. Okay, so we've poured the whole bottle into the funnel. We've closed BV2, then BV4, then SV2. The run tank is just above atmosphere. We might want to pressure. We want to increase the pressure of PR1 again, and then open SV2 briefly just to like pressurize that side of the system to slightly higher at 15 psi instead of maybe 5 psi above atmosphere. Again, at that point, we're checking the nominal pressure and temperature with a special check of like, is the pressure and temperature of the ethanol side, now that it's filled with liquid, still working? Are there any issues with thermocouples when liquid is in contact with them this time? Maybe like check for leaks, just like really obvious high level checks. They shouldn't take forever.
Is there a PT2?
Yeah, that's pressure transducer too. Okay.
Why don't we have a thermocouple in this?
Why don't we have a thermocouple? So we don't think we're going to need a thermocouple, because we can't really imagine this getting to a high enough temperature just from like the sun that it becomes an issue, because if it's really that hot, we're probably not going to be testing on those days, mostly because of the nitrous oxide requirements. If it's really easy to add a thermocouple, that is something that we are open to doing. We wanted to limit the number of additions that we had to this whole thing. So we didn't see like what benefit a thermocouple would bring. Whereas on the nitrous oxide side, it's very clear that we want to measure what the temperature of the liquid nitrous oxide side is to see how close we are and what our buffer is before it turns into a gas, which then does cause problems for us because it just increases in pressure so much. Ethanol does not have that issue. At room temperature, it's a gas. The only serious issue is if it got really hot and I guess maybe started fuming, like off gassing at a higher rate. There's definitely something to be said for that, and we should consider that a little bit more. But it's clear that the nitrous oxide side has a much higher need for a thermocouple. Not that it can only be on one side, but yeah. Okay. Any other questions so far?
I'm glad about that.
I don't know if we've mentioned this, but I'll go through some of these valve things again really quickly. BV is ball valve. NV is needle valve. SV, we already said, is solenoid valve. PT is pressure transducer. RV is pressure relief valve. So RV, particulate filter, is PF. CV is check valve. What you're seeing right there is the burst disc. So those are like worst case scenario. We get to pressures of like 1,000. Our pressure relief valve, like RV1 for example, is stuck. So like it's not even venting at 620. Something goes wrong, or maybe it goes pressure increases so fast that the pressure relief valve cannot keep up. Then these burst discs are kind of our last hope, and they burst at a known pressure with some degree of uncertainty that we take into account. Burst at 1,000, 1,200, something like that, and it bursts before our run tank is, expected to fail, or any of our other components, any of our big components, let's say, are expected to fail. So, okay, TC stands for thermocouple. PR is pressure regulator. Okay, so now we're going to go into our filling of the nitrous oxide. So that's the most dangerous, complicated, long process. So we begin by, I think we're going to want to make sure like everything's closed, right? SV1, SV2 are all closed. But then we're going to open SV1. And now we're going to increase our pressure on that side that SV1 is on. So on the nitrous oxide side, we're going to increase it by increasing PR1, the pressure regulator, up to 820, 850 PSI. The exact number of that needs to take into account the temperature of the day. And the reason is that we want to get to a pressure that nitrous oxide, if at the temperature that it is outside, the ambient temperature, right, let's say it's 20, 25 degrees, that the nitrous oxide will still be a liquid. We do not want it to turn into a gas. And so we're going to pre-fill this with nitrogen, and then when eventually, and we'll get to this later, but eventually we put the nitrous oxide in and open these valves and start letting it flow, instead of the nitrous oxide coming out as a gas and expanding and filling the space, it's already going to be pressurized, so it's just going to come out as liquid. The gas will be in nitrogen, and the liquid will stay as liquid, and it'll flow down into the run tank, and we don't have the situation where the liquid nitrous oxide expands and turns into a gas, and we kind of get some wasted nitrous oxide. Like the nitrous oxide fumes can kind of travel around more. There's a lot of good things that come out of pressurizing before we fill. So we slowly increase that pressure regulator. I don't know how slowly, but we don't want to just crank it. We increase it to 820 PSI, maybe more given the temperature of the day. Then we close SV1. This is important because now at that point, we're going to isolate the system. We do not want SV1 to close or to open again until like we are like done with this process, because we don't want ethanol to ever get close to that like T feeding, close to this SV2, close to the ethanol into the nitrogen tank. We just want to keep it all away from there.
So is there a precondition before you fill nitrous oxide? So is BV2, BV4 open or closed before we put the nitrous in?
We can choose to close those.
Mm-hmm.
I think we have previously already mentioned that at the end of the ethanol filling process, we close BV2, BV4.
And so this entire portion is just closed.
Yeah, there's multiple safety locks there. Okay. So SV1 is closed. Now we're going to start to attach that. Now we're going to attach that nitrous oxide. So we're going to go to the next slide. And we'll see how it looks. So the ethanol, as you can see, is there. In reality, the ethanol bottle that we use to fill up the funnel is taken away at this point, but it is filled. So the ethanol side is filled. You don't have to worry about the ethanol side. We're going to be focusing on the nitrous oxide side. At this point, we thread the nitrous oxide flex hose, so whatever we're using to adapt the nitrous oxide bottle, into the particulate filter, PF3, over here. So there's going to be some kind of connection point, using probably a flexible hose, maybe an adapter, that gets it connected. We want to make sure, I guess, before we do that, to make sure NV1 is closed. It should be closed, that BV3 is closed, that all of these are closed. We don't want it to just start filling right away, but assuming we did everything previously correctly, it should already be closed. So now we're going to open. At this point, the bottle is, the flex hose is threaded on, but the bottle is closed. So we're going to open the nitrous oxide bottle. It might be a ball valve, whatever it is, and we're going to pressurize everything up until NV1. So this side is now pressurized to what the nitrous oxide is pressurized at, and it will be a liquid. The nitrous oxide is expected to be pressurized to about 900 psi. So that's a pretty important number. It's about 900 psi. That's assuming that the nitrogen isn't higher. That's about the maximum that we'll be working with. We want to recognize like that is definitely one of the more dangerous parts, because you will be next to a pipe that is an oxidizer at 900 psi. So this is the part where we're most careful. I want to like think about these processes as best as possible. So they're definitely open to iteration that increases our safety. So we slowly open, and this is pretty important, because there's a pressure difference of 900 to 820. We slowly open NV1, needle valve 1, to begin liquid nitrous oxide flow. We also assume that at this point BV1 is closed and BV3 is open. So we're assuming BV3 is open, and that's what's going to start flow into that whole system. And again, it's just similar to ethanol. It's going to be gravity fed, so that it's coming down, and into the run tank, and eventually stopping when it hits solenoid valve 3. So it's all flowing down from this tank, flowing down, filling all these, and eventually stopping in this run tank, ultimately stopping due to SE3.
So at this point, this tank and this tank have ethanol and nitrogen?
Yes.
Okay, good.
But yeah, they're still separated by SV1 and SV3.
Makes sense.
And SV3 and SV4 are closed. Dang. Okay. I did forget to mention one thing. We're going to, before opening NV1, needle valve 1, to begin the nitrous oxide flow, liquid nitrous oxide flow, we want to record the mass of the nitrous oxide bottle. So before we're here, once we fill this part, we want to record the current mass with this scale of the nitrous oxide bottle, whatever that scale, whatever the method is. And we want to know what the starting mass is, and our final mass wants to be, some known quantity. I think it'll be like 0.3, 0.2, 0.3 kilograms, I want to say, of nitrous oxide difference. So if the bottle weighs, 10 kilograms, after we open this ball valve, let it fill 10V1, we want to open this needle valve 1, and when it hits 9.7, right, 0.3 kilogram difference, we want to close it at that point. We actually want to close BV3 because we think we can close BV3 quickly and just stop flow right there. And then close NV1 just kind of precautionarily. So now I'm saying right here 0.4 kilograms, but in general, we calculate some amount that gives us however much we want to actually fire with, plus anything extra that we want to fill. If we think we need like a little bit extra on the front end and the back end of nitrous oxide because of our ignition process, for example, we also want to take that into account. So we close BV3. And assuming that we actually start at 900 and we get to 0.4 kilograms and we're still driving with a pressure gradient from, it was 820 is what the regulator is set to. And 900 is what the nitrous oxide bottle's at. Assuming that like the nitrous oxide bottle doesn't depressurize quickly and we hit 0.4, great, we're done, we could disconnect the bottle and we'll go on to the next process. But there's a case where, assuming the nitrous oxide bottle does actually depressurize pretty quickly, which means you have a small nitrous oxide bottle, and then the pressures equalize between the two systems, which means there's the flow no longer moves this way, the liquid flow. Then you need to follow the disconnect steps, which I'll talk about in a second. And you're going to have to pressurize the nitrous oxide bottle with nitrogen from, from maybe another tank, ideally from another tank, I would say. Pressurize that back to 900 or back to whatever the maximum safe amount is, and then you could put it back on. And because you're pressurizing it with the gas, that gas will stay on top. It'll push down on the nitrogen, and you'll just get the same benefit of pushing 900 psi into 820, 850, whatever it is, as you did before. So that process needs to be experimented to figure out how easy it'll be. One really important thing that I didn't mention earlier, we already know NV3 has been closed. We want to ensure that BV5 has also been closed. The reason we want to close BV5 and the reason BV5 exists at all is for this filling process specifically, because we know that this system will be pressurized at above 620, which would normally cause this pressure relief valve to go off and lower the pressure. That pressure relief valve is only there for the actual firing process when we're ready, like when we're just about ready to fire, or once we're down to 620 or operating at about 620, where we want to be operating at 620, then we'll open BV5. And that's where, let's say we start the firing process and nitrous oxide begins to heat up, we might want to vent out of that relief valve. During this process, we do not want to vent out of that relief valve. So we're leaving it closed. This, I guess, does remind me, though, if we do want some kind of safety mechanism that's not just a burst disc during our fill process, it's probably a good idea, and I'll make a note of it. So we're going to pause so I can make a quick note. So what we're going to try doing there is probably add an extra pressure relief valve that has above 900 psi or above 1,000 psi, just so that during the fill process, we aren't fully reliant on just a burst disc if something goes wrong and the nitrous oxide does begin to heat up and expand. So now we're going to pause, and I'm going to make a note of that. Okay, so we've just made a note that we probably want to add a relief valve because once we close BB5, we don't really have any backups except for that burst disc, but that's not pictured here, obviously. So we are now ready, assuming that we have reached our 0.4 kilogram goal or 0.3 kilogram goal, whatever it is. BB3 is closed. That's what stops the flow. And we're ready to disconnect the bottle. So the process for disconnecting the bottle is you want to close the bottle, the ball valve on that bottle. And so now you've got liquid nitrous oxide trapped between here. And naturally, some people might want to just unscrew it at that point, but what would happen is as you're unscrewing it, you might just pop it off as it gets to the last thread. 900 psi, not good. So what we want instead is some kind of valve, ball valve, whatever is the cheapest and still somewhat safe. Just a way to use a valve to open and release that 900 psi and then lose some of that nitrous oxide inevitably. But because as long as that ball valve on the bottle is closed and then BB3 is closed, this will vent out, and then you can open that point right there that connects the flex hose to the particulate filter. You might want to, like, as soon as it's depressurized, take into account that we don't want atmosphere to get in, so don't just leave it open. That's definitely something else we'll have to think about. Let me take a note of that as well. Pause. So yeah, what the problem that we just discovered there is that if you don't need to just fill it once, if you fill it once and close BB3, then BB3 is closed forever, or at least until you're done with the test and you don't have any issues with the rest of the test. It'll be fully isolated from atmosphere. However, if you close BB3 and then the goal is to take off nitrous oxide, repressurize it with nitrogen, and then put it back on, a potential concern is that you might open this section of the feed lines to atmosphere, and then when you put the nitrous oxide back in, you have got nitrous oxide mixing with atmosphere, or liquid nitrous oxide mixing with atmosphere before it goes into the feed system, which potentially could cause problems. We would need to research whether that actually is a serious concern, but it is we think it is, which is why we're doing the purging process in the first place. So definitely another thing we'll be looking more into. So more detail on the disconnection process. Let's see if there's anything else. So disconnecting bottle. Close the bottle, open NV1, open ball valve 1, BV1 to depressurize the nitrous oxide bottle between the bottle and the BV3. Then close BV1 immediately. So do not allow air in. That's the only mitigation we have currently. So close BV1 as soon as you feel like it's depressurized, or even in the process of depressurizing, let's say. Then you want to disconnect then you want to disconnect the flex hose that connects the ball valve to the particulate filter PF3. And then you want to move the bottle far away from the test end, assuming you're done with it. So 200 feet away, whatever it is. You do not want it to be near the test end. That's the purpose we have the run tank. It holds the bare minimum, exactly what we need for the test, nothing more. And this big bottle of nitrous oxide is never at risk of a catastrophic explosion. At worst, we have a small explosion. So then we move on to the closing steps of this filling process. While most of these valves are closed, especially any of the ones that are open, that are next to the atmosphere, are definitely closed. And we reduce PR1, pressure regulator 1. So we set it and reduce it to 625 psi, or maybe like 620, 615. I think right now I'm leaning personally toward 615, just under the pressure relief valve. There might be some logical reasons why we need to change that, but it will be in the range of about 600 to 620 psi. And the reason for that is because the next step is to wait for the thermocouple 1 to approach 0 degrees Celsius. Maximum, we want to allow 10 degrees Celsius, but ideally we have thermocouple 1, which is here, which is actually like immersed in nitrous oxide. We want to make sure it gets to 0 degrees Celsius. And the way we're going to get it to 0 degrees Celsius is to have this run tank, and as much of this surface area of the feed system in this area, we want it to be submerged, whatever safely can be submerged, in an ice bath. The ice bath will cool whatever it is from room temperature down to at a minimum of 0 degrees Celsius. And at that point, we can get our minimum pressure from 820, which was at room temperature what liquid nitrous oxide stays liquid at, down to 620, 600, and like really 450 psi, which is what the pressure that's needed to keep nitrous oxide liquid at 0 degrees Celsius. So the reason for that is we want to run our test at about, as low as possible, 600 psi. Is kind of what we've given ourselves as our number, because it gives us a safe buffer of about 10 degrees Celsius above the 450 psi minimum at 0 degrees C. So even if it goes from 0 degrees C to 10 degrees C during the test, because ice melts or because it just heats up in the lines, if it goes from 0 to 10, as long as it's at 600, we're still safely a liquid. So we wait for it to approach 0 degrees C, and then we can open BV5. So at that point, once the liquid is cold again, we open BV5, and this whole line, which was previously at 820 up until this point, will depressurize through that 620 psi valve. So we assume at that point there's nitrogen that is depressurizing, maybe a little bit of nitrous oxide. Ideally, it's all nitrogen that is leaving RV1, relief valve 1, as a gas, bringing it down to 620. We also at that point enable bang or closed loop control of the nitrous oxide pressure. It is critical that we keep nitrous oxide that pressure at 620 or 600. Just we want it to be above really like 580. I'm just saying this range of values, nothing is set in stone. We definitely want to keep it above 540, and our goal is like 600 plus or minus 20. So if it drops down to 580, we think at that point we would do this closed loop control that automatically, or maybe like with a single question, like, okay, are we okay to increase SV1 or open SV1? To open SV1, repressurize up until whatever PR1 is. So let's say I set it to 615. It'll pop up to 615 again, and then close it right away. It's important that we close it right away. Actually, I'm not sure why it's important that we close it right away. It's important that we close it right away because we are worried that if there are nitrous oxide fumes or gas we don't want SV1 to just be open the whole time and allow that gas to migrate into the nitrogen tank and near the ethanol side. So we just want to open it briefly, close it, see if the pressure has risen enough. If it has, great. If not, open it briefly again, close it, and just get it up to the point where it's, 615, 610, whatever we feel comfortable with. In either case, we always want pressure larger here than it is in this section so that there's a gradient, a flow of nitrogen this way rather than nitrous oxide gas and nitrogen this way. Okay. So at that point, I believe you'd be complete with the nitrous oxide filling process. I'm going to take a quick break. Okay, so we just took a break because Chirag had a question about numbers, and he wanted me to go into a little bit of why we chose the numbers we did. I've been throwing around pretty much, I guess, four batches of numbers. The first one is the 0 to 15. Like the 15, that comes from just general pressurization. 15 psig, that's about 1 atmosphere, which is 14.7 psig. When you set something to, 15 psig, which is like 1 atmosphere above atmosphere. So when you set something to 15 psig and you put in, and you have a box that's at 15 psig and there's a little hole, that hole, there's a delta of about 1 atmosphere on each side of that hole. So then that's just for the purging process. And that could be refined as well if we want a faster purge or a more aggressive purge. Then there is the next level up. That next level up is to 450 psi. So these higher numbers are coming from the saturation properties for nitrous oxide. And what that means is, well, we'll move to the next slide and I'll start explaining them as I move them out to the next slide. So if you haven't taken thermodynamics yet and don't know about phase diagrams, what you'll eventually learn, what I'll try to briefly touch on here, is that with water, for example, you can lower the pressure. You can put water in a box and you can lower the pressure to the point where the water will start to like boil. Even though it's not hot, that water, because the pressure is so low in that box, the water will naturally want to go from its liquid state to turning into a gas. So the water, the bubbles will essentially come out of the water and it will vaporize. And that, if you like pull a vacuum, let's say, and half of it's filled with water and the other half is really starting to get limited and there's nothing in there, the water will want to fill that, and it will fill it by turning into a gas and filling that. So what saturation pressure is, you can do the opposite as well. So let's say you had all this water vapor and it was at very low pressure and you want to turn it into a liquid. You can increase the pressure and without changing the temperature, that water will condense and turn back, or that water vapor will condense and turn back into liquid water. So now, assuming that made sense, did that make sense?
Yeah.
You can do the same thing with dinitrogen monoxide or nitrous oxide, N2O. And that's where we start coming up with this next batch of numbers. The lowest temperature that we can easily get it to in an ice bath is 0 degrees Celsius. And so the lowest pressure that we could reasonably operate at that still keeps it at a liquid phase. So the lowest temperature is 0 degrees C. We want it to be a liquid phase, right? This is liquid phase data from this source, is 452. So 450 approximately is like the lowest we can be. If we get to under 450, this liquid nitrogen or nitrous oxide will start turning into a gas. That causes problems because the ratio of the volume that the gas takes up as opposed to a liquid is like a more than a magnitude of an increase. It might be 2 magnitudes even. It's a huge expansion. Liquids are pretty dense, gases not dense, and they'll just expand, and the pressure will increase dramatically if it goes from a liquid to a gas. That might not be true. If it's at 450 and it turns into a liquid, it won't actually increase the pressure. But we are trying to not make bubbly flow, and we are trying to keep most of it liquid because we don't want it for this to be lost as gas if it's venting. Generally, we want our system to be a condensed liquid. So our goal is to keep it at 450, at least, PSI. So then that 450 is actually bumped up to a safe buffer that we're going to give ourselves. And so that buffer that we set is 600 psi. So we give ourselves an extra about 10 degrees Celsius of wiggle room when it comes to temperature.
Oh, okay, so if we were to go up to 15 degrees Celsius, it would be 650. So that's only going to be the plus or minus 20 psi gauge.
The plus or minus 20 is just what level of how often do we want to be checking this? It wasn't a super well thought out number, but if we set it to 600 and then we say plus or minus 20, it does work out nicely that if we go down 20 from 600, we end up at 580, and at that point it's about 10 degrees Celsius, and we know that number. We know that if the thermometer is reading 10 degrees Celsius and we're at 580, that's like, oh no, we're about to start off gassing a lot.
Mm-hmm.
So we definitely want to avoid that point. Any questions with that?
And these are all values we can take at face value, right?
Why? What? Can you explain that question?
For example, at 10 degrees Celsius, it's not going to be 581 or something like that.
Yeah, I trust these values, but we should still have buffers, which is why we still are shooting for 0 degrees Celsius. What really means is we're still shooting for 0 degrees Celsius. We're giving ourselves 10 degrees Celsius buffer. Our goal is to still get it down to 0, which is why we have that ice bath, and we'll be constantly filling that with ice and making sure that there's ice before the test starts.
That's a good addition. Yeah.
Okay. So then the next value going up from 580 or that 600 range that I've been talking about is now 25. That comes from the ambient temperature that we reasonably could expect on one of the worst days of testing. 25 degrees Celsius is, I don't know, 80 degrees Fahrenheit. It's a pretty warm day, I would guess. So given the time that we're doing this at, in April and May. We're hoping that we don't hit that high of temperature. It might be even more than 80 degrees Celsius, but we're hoping that we don't hit that high temperature. But up to 25 degrees Celsius, we can afford to still have a liquid as long as we're pressurized to 820. And so that's why our system is pressurized at the beginning to 820. Because at the beginning, even though we have an ice bath ready to go, the lines and as it's being fed in, there's nothing that actually is going to cool it down right away. It still needs to get to the ice bath. So the lines will be filled with ambient temperature. And so we're kind of accommodating for that ambient temperature and for any like increases in temperature as we're filling by giving ourselves an even higher pressure to fill with. Eventually we're going to drop it down to that lower pressure to fire because that's the pressure that we've been designing around now, about 600. One big takeaway from what you're seeing in front of you, though, is that as the temperature changes a relatively small amount by, human standards, it's not crazy. You'll see that the saturation pressure, the pressure that's required to keep it at a liquid, is pretty dramatically increasing. So nitrous oxide, while it has a lot of benefits, definitely has one drawback of being pretty sensitive or extremely sensitive to temperature, at least, at first glance. I don't really say that relative to anything else. Obviously, one of the main benefits is that we can make it a liquid without going into cryogenic temperatures. So big benefit is that it's not cryogenic, but we do have to deal with a pretty high pressure that increases quickly as the temperature rises at very regular temperature increases. It's not surprising for the temperature increase 5 degrees Celsius, for example, but that would increase our pressure 60, 70 psi. So I think at that point we have covered our filling process. So we can move on, I believe, from these numbers and from what we've been talking about, which is our filling process, onto our less refined, but still worth kind of going over briefly, process of pre-testing and then ignition. So the pre-test process is occurring when the nitrous oxide, ethanol, nitrogen, all of them are filled. It's all pressurized. It's all pressurized to 620, about 600 psi, which is what we've designed our test around, which is what we've designed our nitrous oxide to remain a liquid at because of our temperature ice bath. So we're at 600. We do at some point need to open SV2 to pressurize our ethanol system, which I don't think has officially been pressurized. So we'll have to work that into this operation at some point. Then we want to do kind of a final instrumentation check. So we can't really check valves at this point. It's all pressurized and it's all filled up to every valve. So those are locked in. Hopefully those have been already checked. What we can check though is to make sure our pressure transducers are reading 620 as expected, that our pressure gauges and pressure transducers match, that Our thermocouples are reading expected values. If they're not, either the thermocouple is failing, or more importantly, and kind of the conservative estimate is that there might be something wrong and the temperature is rising, for example, and we need to abort the test and allow it to vent. So kind of a final check. Another great place to put an automated check to just make sure all values are nominal before we begin a test, which will immediately, start changing things. So that's our pre-test. It's right before our hot fire process and our ignition process. So what's happening then, I think we might have already began this process, which was depressurizing down to 625. So we want to make sure depressurize down to 625. We want to make sure that pressure transducer 1, PT1, is between 600 and 615, for example. Those numbers are subject to change as the logic changes just a little bit. It'll still be very much within that range between 580 and 620. If it's below 600 or if it's below 580, again, subject to change based on some of the details, we'll use our closed loop control to activate SV1 to just top off that pressure. Hopefully that's not happening too often. We don't want to just lose nitrogen all the time. We don't want to just, leak this whole time. But if it does happen, we definitely want to just keep it pressurized until we make a conscious decision to vent or to launch and start that ignition process. Final automated check of all the instrumentation, and then we begin the ignition process. That ignition process can be done in a few ways. Right now, we've got two main methods. The first one is a pyrotechnic igniter. Those are similar to what's already used in solid rocketry. It's essentially a sparkler that's put inside of your chamber. It's taped to the back of the engine and is ignited by putting a thin electric wire, or like sometimes they'll actually have wires coming out, by putting a voltage, I believe, across those wires, maybe current, I don't know exactly, and causing it to spark. That spark will, I think those igniters, I think spark igniters is what they're called, rocket igniters. Yeah. They become that sparkler. They have sustained, I think they might have an oxidizer and fuel built into them, ideally. That's kind of what we would want. They have a sustained flame, or not flame, but really like sparkling for 2, 3, 4 seconds. And in that time, once we begin that process, we want to start the oxidizer flow. And then we can go one of two ways. We either have some verification process that a human does that says, okay, I'm starting to see a little bit of a flame from the oxidizer flow, and right away just like keep that test, like give the go ahead on the test. It could be something where it's a dead man switch and it continues to go no matter what, unless they let go of a dead man switch, and then the test automatically shuts down. SV3, SV4 shut down, SV1, SV2 shut down. But assuming that whatever process, it could even be an automated process, says yes, we have the flame catching fire and growing. We didn't just extinguish it by opening SV3 briefly, or like by opening SV3 and letting oxidizer flow in. Assuming that doesn't cause any problems, then we open SV3. Again, the details of this part are not as worked out. So we might just have to open SV1 and SV3 simultaneously. Maybe have SV3 open a fraction of a second early. We want to verify as soon as those are flowing in, we expect combustion to begin a rapid increase in pressure in the combustion engine, thrust starts being measured. If any of those things are not measured very quickly, in a fraction of a second, that means we're just flooding our engine. So we want to immediately shut down the test. So that's where the abort system comes in. So we'd be looking for some of those things. In general, we are very hopeful that like pressure increases red, and maybe a temperature measurement is increased, and thrust is measured. If those things are not measured, especially if none of those things are measured, we have a very big problem because we're flooding our engine, and there might be a sparkler still trying to cause an explosion, which would be a hard start, large pressure increase, and it could break things. So SV3, SV4 have opened. Verify nitrous flow is we've verified that flow is happening. We're getting combustion. Maybe that's the point where we open SV4 and SV1 and SV2. The difference between opening SV3 and SV4 and then opening SV1 and SV2 should not be a large difference in terms of time. They should be happening pretty close to each other, so that verification process should be very quick, or should be designed to be very quick. Theoretically, if we were to open SV3 and SV4, just to clarify, we would eventually run out of gas if we were not, or we would run out of driving force or driving pressure if we were to keep SV1 and SV2 closed. The reason we open SV1 and SV2, and it's okay to open them simultaneously and kind of allow that whole system to be open, is that nitrogen at that point would be the driving force, and we'd have flow going from this point in this bottle, really driving any nitrous oxide that's left in this tank or in this tank along that feed line, and same here. It'd be really driving it, so the flow gradient is like clearly moving away from this T-fitting in this section, which is kind of a danger zone for if they were to mix. That's why we've got that check valve there, and we're also designed so that we don't think the ethanol will need a check valve. That might be something that we do eventually add as an extra safety precaution.
There's a check.
Yeah, there are check valves here in case there's a hard start that pushes propellant back up into the feed system. So yeah, we think CV2 will do a good enough job, and there shouldn't be anything beyond CV2 that could cause a significant enough pressure rise that would interfere with the rest of the system, but it's definitely worth consideration, adding a check valve right in this area. So then we're going through our high fire process. We are checking constantly for abort triggers, anything that could be interpreted as like incoming failure, upcoming failure. We want to have that instrumentation be read and then trigger an abort. Again, I went on this tangent about SV1, SV4, or SV1 and SV2 opening so that we could drive pressure. And then once we are done, and we have a sense that nitrous oxide has been fully extended, and like we've run out of it, and ethanol ideally as well extended, so we want both of them to be completely empty. Once we are confident that it's empty, either through like the scale measurement, or we start noticing that thrust has dropped significantly, then we close SV1 and SV2. We do not close SV3 and SV4 yet, because in case there's a little bit left, we want this system to kind of drain out whatever's left. So we're letting it drain out. That might not be necessary. Either way, eventually SV3 and SV4 do close, and we want to make sure they close ideally again while there's still nitrogen in the system and it's being purged, not after the test like 15 minutes and atmosphere is able to get back in. We still want to keep the system relatively clean so we don't have to do some big purge, or we can just run a next test by some easy way of filling this nitrous oxide again. So we close SE1 and SE2 after firing. We close SE3, SE4 to stop any purging and then maintain that clean nitrogen environment internally. Okay. So I think that is a full overview of the current state of our feed system as of like week 7, I believe, winter quarter for the rocket engine Capstone team for Rose Propulsion Lab. Thank you for watching if you're still watching. Yeah.
Okay.
If you do have questions, we will probably leave some contact information with the details of wherever this video is posted. So, any final questions, Chirag, based on what I just shared?
No questions. I think this covers everything.
Okay. Unlikely. Maybe.